In section 2.2, we looked at graphs of functions and really began using the notation for a function as instead of writing ordered pairs as x, y, we write them now as x, f of x. And we also have another interpretation of what f of x is. It's not just a function value, you can also think of it as the height of a point from the x-axis. So f of x is the same as that height. So for example, the f of 2 is that height and f of 1 is that height. Of course, if you want to know the y value, you just go straight across to the y-axis, and that's where the y value is. The y value is the same as f of x. I did the demo in Sophia for you. You might want to experiment with some other functions besides this one. So for example, you could experiment with f of x equals x plus c. You could experiment with f of x equals c times x and see what happens there. And you might want to let c have values that are both positive and negative. So you may want to just experiment with a few more families of functions just in your spare time for fun. And let's see, these common function types, you're already familiar very much with the linear function, y equals mx plus b, constant function, y is equal to c, that's your horizontal line. Remember, it has slope 0. Power functions, x to a power, where the power has to be a positive integer. So the powers that are positive integers are 1, 2, 3, 4, and so on. So those kind. Absolute value function, again, one you're already familiar with, and then we studied a little bit about the greatest integer function in this section. So as we progress, you'll see some examples with that function. In fact, so here's our first problem. It has to do with the utility rates of Westside Energy, what it charges its customers. A base rate of $6 a month, and then 10 cents per kilowatt hour for the first 300 kilowatt hours used, and then 6 cents per kilowatt hour for all the usage over 300. And so we want to express that monthly cost as a piecewise function. So this problem is not impossible. So X is the number of kilowatt hours of electricity that's used in 1 month. So let's suppose that we want to find out what the monthly cost E is, and it's going to be a piecewise defined function. So it depends on how many kilowatt hours we have, because we have a base rate of $6 per month. So everybody pays $6 per month. So I'll just write $6.00. Okay, but 10 cents per kilowatt hour for the first 300 kilowatt hours used. So if the kilowatt hours are between 0 and let's see, the kilowatt hours is X is the number of kilowatt hours, and let's see, less than, so I have to move that over a bit, less than or equal to 300, then it's 10 cents per kilowatt hour, so plus 10 cents is $0.01 times the number of kilowatt hours between 0 and 300. But once x is greater than 300, we have to change the way we calculate our charges. We still, of course, have to pay the $6, so we still have $6. But now the cost of the kilowatt hours here is different because we're using more. So we're being charged now 6 cents per kilowatt hour. So we're being charged less for the kilowatt hours over 300. And so that means that to the $6 we have to add 6 cents, which is $0.06. But now it's not times x, because remember, we're only going to use this for the hours over 300, for kilowatt hours more than 300. So we're not going to count all 300, we're just going to take 300, actually we're going to take, so for the x kilowatt hours that we use, we have to subtract those first 300 because we're not paying the 6 cent rate for those first 300. We're only paying the 6 cent rate for anything more than 600 or more than 300. So x is greater than 300, so x minus 300 will always be greater than 0. And that's how we figure out our charges for the kilowatt hours over more than 300. This is a piecewise function because the domain, and you see the domain here, is from 0 to 300 inclusive and then greater than 300. So the domain is actually all real numbers, or you can indicate that as minus infinity to infinity. That's all real numbers. It's just split into two pieces, and that's why it's called a piecewise function. It's a piecewise function because the domain is split into two pieces, and that determines how you calculate the value of x, the part of the domain that you're in. So the graph of the function I will leave to you because they're both just lines, and you should be able to do the graphs of lines quite easily. So remember, this is expected to be done. You should graph this line, but you have to stop it for x values between 0 and 300, and then you have to jump off that line and graph this line instead for all the x's greater than 300. So here's another function defined piecewise right here. You might want to experiment and do the graph of that. We also learned about the vertical line test, which is something that you're probably all familiar with. So if you imagine passing a vertical line through through any of these graphs, pass any vertical line through this graph, it only intersects the graph one time, so that one is a function. But this one, you can see the vertical line intersects the graph in more than one point, in several locations, many locations, infinitely many in fact, so that's not a function. This one is a function. Actually, what's happening here is this part is just continuing down and getting closer to the y-axis but never touching it. And similarly right here, getting closer to the x-axis but never touching. Same thing here, same thing here. So this is a function. In other words, this is a function. This is not the graph of a function. Here you go right there, that vertical line right there makes it not a function. And that does, and all of these make it not a function. So vertical line test for functions is very important. To determine whether an equation defines a function, you can solve it. If you can solve it for y and get a unique y equals, then you have a function. So solving this for y means that we have 2y equals 4 minus x squared, and so therefore y equals 4 minus x squared over 2, which you can rewrite as 2 minus 1/2 x squared to get it in standard form. And so you can see that you solved for y, therefore that's a function. However, this next one, x squared plus y squared equals 9, if you solve for y, first you'll get y squared equals 9 minus x squared. But now you have troubles, because when you solve this, when you take the square root of both sides, you get the positive or negative square root of 9 minus x squared. So that means that for any x value that you have, so if you pick any x value at all, say you pick this x value, that's in the domain of this function, then you'll get a plus y, which means you'll be up here somewhere, and then you'll get the minus y, which means you'll be down there. Well then, clearly this will not be a function, because you can see that there is a vertical line that crosses those 2 points. So this is not a function. Not a function. You can tell that because you can't solve it for y, for a unique y. Okay, then the next thing you learned how to do was to find the domain and range of functions from their pictures. So the domain is the set of all x values, so this is implied to go on forever. So your left endpoint here is going to be minus infinity. And then if you are crossing along the x-axis here, you'll see that no matter where you are along the x-axis, you can always find a point that has that x-coordinate, so that's the domain. The range is different because the range is from the viewpoint of the y-axis. So if you're on the y-axis, you're only going to see points on the graph for y values between -2 and +2. So the range is the set of y values between -2 and +2. For this next one, the domain, again, this is implied to go on forever, so it's minus infinity. Now if you're on the x-axis, you're just walking along the x-axis, boom, 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 you're going to see points in the graph all the time. You can look up and see those points. You can still look up and see points. Now you have to look down and see points. And you look down and see points. So you see points all along the x-axis. So minus infinity to infinity is the domain. That should be a comma right there. I don't know what that is. The range is different. Again, you're looking from the perspective of the y-axis, so you don't see any points on the graph until you get to this y value, which is -2. But between -2 and -1, you don't see any points on the graph. So negative 2 is a single number. A single number we put in set symbols. It should be negative 2 in set symbols. It's a single number. Then union. You don't see another point until you get to 1. Then after you get to 1 on the, or negative 1 on the y-axis, you can continue to see points all the way until you get up to positive 2. So now we can use interval notation, because that's an interval, negative 1 to 2. So those are our, that's the range. The range is a single number and then an interval. I'll let you do the last one on your own. It has that break in the range, so I'll let you practice doing that. Make sure that you know the graphs of the basic functions, the power functions, when the exponent is even or odd. You can see that the even exponent functions have similar graphs, just a little flattened out as the exponent gets greater. And the odd ones have similar graphs as well, but just sort of broadened out there near the origin as the exponent gets bigger. These are reciprocal functions. Again, even exponent and odd exponent. Make sure you notice the differences and the similarities. Then there's root functions like the nth root. There's square roots, and then there's cube roots. So again, depends on whether that's an even root or an odd root. So look at similarities there. There's a fourth root and a fifth root for you. And then there's the Auxey value function. And then finally, the greatest integer function. So be familiar with all those different types of graphs.